Find the maximum value in dollars. In this problem, a knapsack having a total weight capacity of 100 pounds can be filled with items A, B, and C. The variable xi represents the quantity of each item A, B, and C in the knapsack. Variable vi represents the value of each item A, B, and C in dollars. And variable wi represents the weight associated with each item A, B, and C in pounds. The quantity of each item placed in the knapsack, xi, is constrained to be non-negative and an integer value. Since this is an unbounded knapsack problem, there is no maximum constraint on xi, but there is a constraint on the total weight. The question asks to find the maximum total value of the knapsack. Therefore, we'll have to determine the quantities for xa, xb, and xc which maximize the total value in the knapsack based on their values and weights. To begin, we'll divide the problem into three separate subproblems, which are: how many items A should I add to the knapsack, how many of item B should I add to the knapsack, and how many of item C should I add to the knapsack. Based on the weight of each item and the weight capacity of the knapsack, we can compute the maximum value xa equals 5, because if xa equals 6, then the maximum weight constraint of 100 pounds would be violated. Similarly, we can compute the maximum values for xb and xc as well. In order to make the drawing more accurate, we'll add a few more items. Based on the quantity range for xa, xb, and xc, we'll set up a block diagram which divides the overall decision process into three stages: Stage 1, Stage 2, and Stage 3. At these three stages, we'll determine the values of decision variables xa, xb, and xc. Certain solutions will exceed the weight capacity of the knapsack and be infeasible, while other solutions will not use enough of the available weight capacity and have a smaller than optimal value. First, we'll focus in on Stage 1, because we'll use the forward-reaching DP algorithm, which asks, from the given state, what is the optimal feasible knapsack in the previous state to come from? Since the previous state only contains an empty knapsack, there is only one beginning state to come from. Therefore, all 6 of the xa shall come from the beginning state. This is a trivial step. Next, we'll modify our boxes to track the decision variable xi as before, as well as the weight wi in pounds, which is our state variable, as well as track the value of the contents in the knapsack vi in dollars. After applying this new format and solving for the weights and values, we notice, for example, filling up the knapsack with 2 units of item A will use up 36 pounds of capacity and provide a value of $60. 4 units of item A will use up 72 pounds of capacity and provide a value of $120. Next, we'll move on to Stage 2, where we can select 0, 1, or 2 of item B to place into the knapsack. Also note, each item B weighs 35 pounds. As with the previous stage, we again ask the question, which knapsack from the previous state should we come from, to obtain an optimal knapsack value and not violate the maximum weight requirement. If we consider xb equal to 0, then the weight is 0, which means we should choose to come from the knapsack in state 1 with the largest value of VA, which doesn't exceed a weight of 100 pounds. Since no knapsack exceeds a weight of 100 pounds, we'll select the top knapsack, which corresponds to XA equal to 5, for XB equal to 0. If we combine the boxes, we can total the weights and values, which again equal 90 pounds and $150 in our knapsack. Next, we'll assume the knapsack contains item B of quantity 1. Now the knapsack already weighs 35 pounds. Therefore, we must choose the state 1 knapsack with the highest value, which has a weight WA of at most 65 pounds, which is when XA equals 3. 3 of item A and 1 of item B results in a total weight of 89 pounds and a total value of $150. Lastly, we'll solve for XB equal to 2, which means choosing the box from state 1 with the greatest value VA, which doesn't exceed a weight of 30 pounds. Therefore, we choose XA equal to 1. And this knapsack adds up to 88 pounds in weight and $150 in value. Now we'll compare all 3 knapsacks after stage 2. All 3 knapsacks have a value of $150, but all 3 combinations leave at least 10 pounds of weight capacity unused. In dynamic programming, there are usually tie-breaking procedures, such as if the greatest value knapsack combination is non-unique, then the knapsack with the lightest weight is the preferred combination. Looking back at our possible solutions, we know the greatest value is at least $150 and may be more depending on stage 3. Moving on to the third and final stage, as before, we'll start at each value of X3 and from there determine which knapsack from state 2 should be used to maximize the total value in less than 100 pounds. The apparent dilemma is that the current knapsacks are all too heavy to add item C, even once. To solve this problem, we'll need to unpack our optimal state 2 knapsacks in order to provide adequate weight capacity for the weight of item C, WC. How much should we unpack from each knapsack will depend on the weight capacity, WC. Let's begin by unpacking the first knapsack, where XB equals 2. If we remove item A, the knapsack is only 70 pounds and has a value of $120. If instead we remove 1 of item B, the knapsack would only weigh 53 pounds and have a value of $90. Removing 1 of item A and 1 of item B, the knapsack would weigh 35 pounds and have a value of $60. Removing both B items would result in the weight of 18 pounds and a value of $30. And completely unpacking the knapsack would result in 0 weight and 0 value. For the time being, we'll preserve the total from each knapsack and return to stage 3. Starting with XC equal to 0, we want to find the knapsack containing items A and B, which has the greatest value and has the weight less than 100 pounds. Therefore, the top row would result in the optimal solution. Combining this row with our row for XC equal to 0, we can see the weight and value contributions from all items in the knapsack. Next, if there is 1 item C in the knapsack, it will contribute 14 pounds in weight and $20 in value. The combination of items in the knapsack having the largest value but having a weight of at most 86 pounds is the second row, which corresponds to unpacking 1 item A. to make room for the one item C. In this combination, the total weight is 84 pounds and the total value is $140. For XC equal to 3, we again choose the same 70-pound knapsack, which results in a total weight of 98 pounds and a total value of $160. This process continues for XC equal to 3 through XC equal to 7. For XC equal to 3, the total weight is 95 pounds for a value of $150. For XC equal to 4 and 5, the weights equal 91 and 88 pounds, and their optimal values equal $140 and $130, respectively. And the final results for XC equal to 6 and XC equal to 7 are also shown. At this point, we've determined the optimal knapsack combinations from unpacking our optimal knapsack where XB equals 2 in state 2. And we have recorded the optimal values and the contents in the knapsack. However, in the forward-reaching algorithm, we start at the future state and ask, which knapsack in the previous state should I come from in order to maximize the value of the knapsack? We'll ask the question for all 8 possible values of XC, and the combination with the greatest value will be optimal. Therefore, we need to unpack the optimal knapsacks for XB equal to 1 and XB equal to 0 in state 2, as we did with XB equal to 2, to ensure that no potentially optimal solutions go unevaluated. We'll begin by unpacking the optimal knapsack for XB equal to 1. This time, there are 4 total items to unpack, which will result in 8 unique combination of items in the knapsack. For example, we can unpack none of the items or unpack all of the items. We can unpack 1 of item A or 1 of item B or 2 of item A or 1 of item A and 1 of item B or 3 of item A or 2 of item A and 1 of item B. After looking at these weights and values, we notice 2 combinations yield a value of $90, and another 2 combinations yield a value of $60. If 2 unique combinations yield the same value, we'll break the tie by choosing the lighter knapsack, which is the dominant alternative. This is the first of 3 outranking criterion. We would also remove knapsack I if knapsack J had equal weight and a higher value, or if knapsack J had a lower weight and a higher value. Ruling out knapsack combinations one stage at a time, which are not part of the optimal solution, is a major advantage to the dynamic programming algorithm. After matching the unpacked knapsacks with all 8 values of XC, we can again report the optimal knapsack contents for XC equal to 0, XC equal to 1, XC equal to 2, XC equal to 3, XC equal to 4, XC equal to 5, XC equal to 6, and XC equal to 7 for the optimal knapsack in state 2 where XB equals 1. Lastly, we'll evaluate the solutions where the optimal knapsack XB in state 2 equals 0. After we do, we'll have all the data we need to complete stage 3. For XC equal to 0, the maximum value for all 3 knapsacks is $150. So we'll choose the combination with the lowest weight, 88 pounds. For XC equal to 1, the maximum value is $140 in each case. So we'll choose the lightest combination, which is 84 pounds. For XC equal to 2, The maximum value is, again, a three-way tie, this time at $160, where the lightest knapsack is 98 pounds. Similarly, the remaining X states are computed the same way. The maximum value that can fit in the knapsack is $160 by including 0 of item A, 2 of item B, and 2 of item C. When reviewing the possible solutions, the answer is C.